So we've looked at a spring mass system before, where we had a spring, we had a horizontal surface, and we had a mass lying here, and this was frictionless. And one question is, if we had a vertical spring mass system, so now we have a spring, the mass is hanging off the spring. Is this more complicated because there's gravity? And there's two scenarios. So one is you calculate this as your zero displacement in the vertical direction. And then the other scenario is you hang the mass off, you let it stretch a little. So the spring's going to stretch a little bit because you've got a mass here. And let's say it comes to rest here. Now you think of this as your zero. Is there a difference between these two scenarios? Let's look at the first one. So the first one has a force of gravity and then a force from the spring. And we talked about Hooke's law before. So the force from the spring was negative ky. We're going to call this y1. And then the force of gravity, so let's say, because we're moving down first, so we'll call that direction positive, is mg. And then that is, by Newton's second law, mass times acceleration, which is the double derivative of your displacement variable, which we're calling y1 here. So that's the first one. In the second one, we've already taken care of gravity. So your mass times your acceleration, we'll call this displacement variable y, as opposed to y1. They're going to be different. Y double prime is just negative ky. Your gravity is counteracted by the amount that the spring is being pulled on. So there's no extra gravity here. Let's look at what the difference here is. If I just go into this equation, equation 1, and I'm just going to sub y1 equals y plus mg over k. They're just going to be separated by some vertical distance. Then what happens? Then y1 prime is y prime. This is just a constant. Mass, gravity, and the spring constant are all constants. So they go away when you take a derivative. Y1 double prime equals y double prime. And now we can sub those into 1. So m, we're going to replace y1 prime, y1 double prime with y double prime equals negative k. We're going to replace y1 with this expression over here, y plus mg over k plus mg. And then what happens? We distribute the negative k, get negative k y. Negative k times this is minus mg, and then we get a plus mg. These cancel, so we get m y double prime equals negative ky, and that is exactly equation 2. So what have we realized is that y1 and y are just separated by this vertical distance, and that is in fact this vertical distance from the center of this mass to the center of this mass, or top to top, bottom to bottom, doesn't matter. Center to center is probably makes the most sense. That vertical distance is mg over k. So actually, if you took a mass, attached it to a spring, and you knew how heavy it was, the amount that it gets displaced before it comes to rest again, you could use that distance to calculate k if you don't know what k is. So that's kind of cool. Okay, because these two equations therefore are equivalent, we're just going to go with equation 2 because it's easier to deal with. It's an easier differential equation to solve. It's homogeneous. Okay, so let's solve it. What happens? The characteristic equation, let's collect it all on one side first, actually. My double prime plus ky equals 0. Now the characteristic equation is mr squared. We're going to solve it with letters, but it's going to be okay. So m and k are constants, remember. And by definition, because of this negative sign, we've defined k to be greater than 0, and of course m is a mass, so m is greater than 0. What does that mean? That means we have complex roots. because then r is going to be plus or minus the root of negative k over m, or k over m, and then there's an I outside. What does that mean? That means when we write down our general solution, that e to the real part times t, there's a 0 there, so it's e to the 1. So there's no e term. It's just going to be cosine and sine. So we'll have c1 cosine of the root of k over mt plus c2 sine root of k over mt. Okay, and that's a little bit ugly, so we're going to introduce a new constant. So let w naught be the root of k over m, and then we can make this look a little bit better. c1 cosine w naught t plus c2 sine w naught t. Okay. This equation is good for solving for c1 and c2. It's easy to plug stuff into. It's bad for graphing. So we're going to convert it a little bit for graphing. We are going to remember this because we'll use this for plugging stuff in. But we'll also get something else. So let's look at the reason it's bad for graphing is that I can graph a single cosine or a single sine, but then adding them together is hard. I don't know what that looks like. So there's these formulas that I would have told you to memorize in pre-calculus, but your teacher probably didn't. Cosine, the relevant ones, you can do this with either a plus or minus here, but easy ones are minus with cosine and plus with sine. So this is cosine A, cosine B, plus, so the cosine will change the sign in the formulas, sine A, sine B. And then sine A plus B is just sine A, cosine B, plus sine B, cosine A. I would have chosen to use the second one because everything's positive. Sine is nicer. Depending on the textbook, you'll see either sine or cosine. Your WebAssign often has cosine, so we're going to do it with cosine. But that means there's going to be a negative inside once we finish up with it. Okay, so what I would like to introduce is I would like my C1 to be cosine of some angle times some number, and C2 to be sine of the same angle times some number. That way I can factor out that number. It's going to be the same number. And then I'm going to be able to use this formula to write the whole thing as a single cosine. Okay, how do we do that? Let's actually do this graphically. So we're going to graph this point, C1 comma C2. And then I can draw basically going to be a right angle triangle. So C1, C2. And this is how I'm going to introduce a cosine and sine here. So if we call that angle there delta, I can shrink this point down to the unit circle. So this hypotenuse is the root of C1 squared plus C2 squared. So if I divide both of those, then I get this point, which is going to be the point. So I'm dividing each coordinate by that hypotenuse so that I turn my hypotenuse into 1, meaning I'm going to land on a circle of radius 1. C2 over the root of C1 squared plus C2 squared. I've shrunk it down, and now this point also equals cosine delta sine delta. That's the definition of a point on a unit circle. This is actually what I take the definition of sine and cosine to be. You may have learned it differently. I think thinking about it this way is better. Okay, so what does that mean? That means my cosine delta is this number, and my sine delta is this number. So I'm actually, for once, going to make this equation uglier. So I'm going to factor out a root C1 squared plus C2 squared. I didn't actually have that here, so when I factor it out, it shows up in the denominator. I'm going to get C1, the root of C1 squared plus C2 squared, cosine omega naught t. So everything here is the same. And once I distribute this, I should get back to this equation. Plus C2 over the root of C1 squared plus C2 squared, sine of omega naught t. Okay. And then what happens? This guy is actually cosine delta. This guy is actually sine delta. So y equals, I have this ugly thing out here still. But now I have cosine delta, cosine omega t, omega naught t, plus sine delta, sine omega naught t. And it doesn't matter what order these are in. I can swap them. Cosine, fun fact, cosine b minus a is the same as cosine a minus b. Check that out. That's just because on the unit circle, if you reflect, so you make the angle negative, the x-coordinate is the same. Okay, so it doesn't matter what order I take these in. I'm going to write it in the order that you'll often see in textbooks and that you'll see on your WebAssign. So this is the root of c1 squared plus c2 squared cosine of omega t minus delta. Could have been delta minus omega t. Doesn't matter. I can swap the order of these guys. Okay, and then they normally replace this with a letter 2. So maybe we'll let c, I haven't used c by itself yet, equals the root of c1 squared plus c2 squared. And so then let me give it a little more space. Y equals c times cosine of omega naught t minus delta. This one's easier to graph. This one's easier to solve for constants. If I solve for c1 and c2, I can solve for c and delta, right? I have, okay, c is easy. I've got this equation. Delta is a little bit annoying. The easiest way to do this is to take a ratio. So we'll take the ratio of the y-coordinate to the x-coordinate, and then we'll get tan delta, because sine delta over cosine delta is tan delta. And then I got these big ugly fractions, but they both have the same denominator. So if I multiply top and bottom by the same thing, they go away. This is tan delta equals c2 over c1. And then you just have to be careful. If you take a tan inverse or an arctan, the one that's in favor goes back and forth. I think the one that's in favor right now is arctan. If you take an arctan, you might run into domain issues. So on the unit circle, tangent, let's see, tangent is a really big negative number here, goes to 0 here, and then goes to a really big positive number here. So the range of arctan is negative pi over 2 to pi over 2. So just be careful. You've got to look geometrically to see what you're expecting. Are you expecting angles in this range, negative pi over 2 to pi over 2, or are you expecting them somewhere else? Especially this half of the circle won't by default get chosen. So you've got some domain considerations there.